Okay, so we talked about position, we talked about speed, we talked about I need to turn on my overhead projector. That's what I did. What? Oh, that light stays on low. So you can see how to turn it on at night. We had a projector in here where the remote stopped working, so we had a long stick that we reached with. It was our remote. Position, speed, we talked about weight, force, we talked about pressure, didn't do count. Counts are, it's more of an indicator. You know, normally a count, we use another sensor like a limit switch or a proximity switch to input into a counter. So it's more of a piece of instrument than an actual sensor. So it depends on the sensor. Talk about temperature, light, talk about liquid levels, motion, proximity. These other ones get a little more complicated. So we've done a really good job. Standard units of flow. We have the standard, using the standard or SI units. Standard liters per minute, cubic meters per minute, cubic meters per second, and then down below that you might see the gauge M3 over seconds. And then centimeters per minute, standard centimeters. This customary though, what do we use? Or, and there's another one too, I should have put up there, gallons per minute and then gallons per hour. Now you'll see that a lot, especially in big flows. And then cubic feet per second. And so this is what the indicator is going to display, right? And these are just some typical gauges I pull up and see if I can put some of them up here. I look up and see them. Here's gallon per minute, gallon per hour, liter per minute. This is gallons per minute, and this is gallons per minute. So this was one picture, so they didn't get all of them up there. There is liters per minute up there, though. Flow sensors are based either on a pressure base, and that I should go back. It's a pressure differential. You look at the orifice place, the Ventura, and then pedostatic, rotometers, spring and piston, turbines, paddle wheels, vanes, magnetic, and ultrasonic. So these are the ones we'll go over. Some of them we've already talked about, and easy to see what they do. This is a spring and piston. So basically, how does it work? I mean, calibrate spring. Yeah, we have calibrate spring. We push up against an object. It pushes against the spring. Spring is calibrated, and then we can come up here and measure this position, this right here, and that would give us a good indication of what? Flow rate. Yeah, the flow rate. Yeah. So here we're taking a pressure and converting it into something that indicates flow, right? You'll understand that. So a lot of times we use pressure because pressure can be calibrated. This is a orifice plate flow sensor. Basically, we just put an orifice in there. What it does, it creates a high pressure side and it creates a low pressure side. And we use a differential pressure sensor to go across those two outputs. And the differential pressure would be calculated at flow. Okay. This usually takes a little math. The indicators have to, either it's going to be like inches of mercury, so that's used a lot. Or they use inches of mercury, right, to understand the different pressures will push it up. If we're going to go into like a computer, then there's a lot of math involved to go from what? Pressure to flow. So a lot of these indicators are pretty small. This is a Ventura, not a Venturi, a Ventura. And notice I put my thing on the center, but we have pressure 1, pressure 2, and then the fiber that it goes through actually has a Ventura in the center. So what happens is when it goes through there, it speeds up, then it actually Anybody got a pressure washer? Yeah, and you got that suds in there, right? You understand? And where do you hook that sucker up? You hook it right there. And when that fluid goes flying past there, it gives a low pressure here, high pressure there. And if we can create something that's lower than atmospheric pressure, then that's a lot. So vacuum. So vacuum is anything below what? Atmospheric pressure. You understand that? I think we've already talked about that. So this is the way they generate the vacuum over in on the Armatro line, and also the Festo line. We have a little unit that converts a pressure over to a vacuum. And what they do is they just blow the air through that Ventura, and they put the little vacuum where right there in the center. So they're not measuring flow. All they're doing is creating a vacuum. But if we got a reference, and then we got the flow, so we reference the side before it goes through the Ventura, right? And then we do what? Then we reference at the Ventura, and the pressure differential would be proportional to the flow rate. Is that liquids or gases or fluids? Well, for fluid can't be for anything. Well, for fluids, it's got to move. So yeah, we could use this thing on gas, we could use it on pressure, and that's a perfect example. Of course, over there, they're not using this side, they're using this side, right? Understand that. And then the other side is being into atmosphere, and then when it goes through there, it creates a low pressure. You can hear it blow out, it just comes straight through there, and blows out on one side. These things make a pretty good deal of noise, because they just vent the air on that side, right? Make sense? You okay? This is a PDOT tube. So here it's basically the same thing. We put high pressure into the PDOT tube. We reference the static tube to the other pressure. We learned these real fast when we worked on airplanes. They had PDOT static tube on there, and that's the way they gauge not only airspeed, but that's the way they gauge altitude. The problem is if we just use pressure and we get up to 35,000 feet and get altitude, it means nothing, right? You understand? Because what happens when we go up in the air? Well, pressure gets what? Less. But if you have a reference to where you're at, and then compare that against the amount of pressure coming into your PDOT tube, then they could. So they use this thing to get barometric altitude. Of course, they had radar too, but you just barometric altitude as a backup, and also they use this for airspeed. They don't mean anything unless you're jamming that thing in the PDOT tube. And our PDOT tubes are heated. Yeah, they had to be heated because if you get heat up, you get up to 35,000 feet, the PDOT tube is freeze up. And the props were heated. They had turbo props on there. The props were heated. And the leading edge of the wing had heat on it to keep them from more icing over here. The tail. And the leading edge is the tail and the fins of the elevator. We didn't want those to freeze up. We did lose one of our. We almost got the commander almost got in trouble. We had one of the. So what they did, they had a set of brushes, about 6 of them, that would transfer power over to them. So they had slip rings and brushes, and they would transfer power from the plane into the heaters on the leading edge of the props. We had one bust off on us, and we flew that plane right heating on the props. Because we were out in Diego Garcia, it's a little island in the ocean, and we didn't want to stay there. So it was either wait, I never forgot how long before they could get that to it, a new prop to it that actually broke the prop. Not the prop, the heating strip that went down the prop came out of the rubber boot. And we just went out there and peeled it on out and cut it off. And I never forgot how long it would take to get the prop out there because you had to have special tools to replace it anyway. It's going to be like 2 or 3 months, and we said, Commander said, we leave in this place. Because Diego Garcia wasn't what it is then. So, PDOT static, so what we do is we force it in, you can't see the static tubes on the side. So we have a PDOT, which takes direct pressure, static tube, which gives us what? Reference pressure, and these guys sense flow. They not only can sense flow, well, airspeed would be what? Flow. We had a guy, this is back in my early days, my drink, where we would have, they had candles on the table. And we would see whoever could put it out with their hand, everybody would buy him a beer. And we had a guy that burned his hand real bad. You know, he told his wife. So he grabbed one of those PDOT tubes with the heater turned on. This is a rotometer. So on rotometer, what we do is we use gravity. These things mount vertical. And then we put flow through here, right? Y'all understand that? And then this is calibrated. It's perfectly sized. It's machined, and it has a precise weight. And what it does, depending on the amount of flow, is where the weight of the instrument is going to do what? Match the weight of the flow, or how much it's pushing against there. All right, it's actually doing pressure, right? So the pressure of the flow, but the pressure of the pressure is directly related to the rate of flow, right? We use these guys all over the place. So that was basically that thing. I did a little plastic tube. So these things always mount vertical. And you can, if you look at it, you can see the little, the graduation go, well, you can see the graduation on the side, but if you look at the tier tube on the inside, you'll see that it makes a lot. Yeah, it makes a big. Rotometer is based on gravity, height of the flow, it indicates the what? Yeah, the rate of flow. So if we can measure the height of this, so how can we convert this over to an electrical system? We could definitely do it digital, right? Real easy, especially if these are clear. We could shoot like a through the beam sensor through there, and when the flow come up and broke the beam, or we could graduate it in different places and look when it reads something. It's an analog, it shows analog. A lot of people like it because it's the scales on a rotometer that scale or linear. I mean, they don't, so which means the space in between the scales wall. Yeah, they're equal. It's kind of like a speedometer on your car, you know, it's a linear scale. So a lot of times you can understand your speed without looking directly at the wall. At the meter, yeah, your speedometer, because if you drive a car long enough, you basically know how it's. So if it's in the center, you know you're doing about half of what your car is. This is a vane. I like this one because you can see what they're using as a sensitive element now. Yeah, they're using the potentiometer. So what we do with a vane is we come in here, we put pressure against it, right? And then, of course, it's calibrated, and when it pushes against the vane, what does that do? So the distance the vane moves back will give us an indication of flow. Now, the problem with these, go ahead. That's fine. It's still a vane. It's still a vane type thing, right? A lot of your, I don't know, some of your vehicles, so this is not, I don't know, I guess since it's got a potentiometer, they could actually use this to control the flow from your pump, yeah. But, okay, this is pretty easy to see how it works, the way I understand this guy. So all we do is bring the flow in to one side, and what to do, well, this is what we call a paddle wheel meter. Very easy to see how this works. So the faster it turns, the faster the flow. This is a turbine flow meter, which works exactly on the same principle. Here what they're doing is they have a magnet on one of the blades, and then they have a Hall effect sensor in the sense, so this would be the whole sensor together. Then they use the Hall effect sensor, which is, on this one, it's back here. So if the shaft spins, then we could easily pick it up back here, right? And what does the Hall effect sensor do? It's the magnetic field. So here, the rate that those pulses come would be a direct indication of flow rate.
What's that, that chamber, to the left of the, say, fella?
Don't know. This looks like it's probably in there. I don't know which way the flow comes in. The problem is that we call it luminary flow. I imagine that's what it is. Luminary flow means it's flow moving in one direction. Then we have these, what they call the other one, the one that runs against the side. In water, we call it eddy currents. So if we move something and then it's in motion, it has a tendency to put a turbulence in there. So it looks like to me what this does is take the spinning effect of the rotor and then turn it back into luminary flow. What it looks like. What it actually does. If that sounds good. I can't think of anything else. So notice it's got a cone right here that takes the center and brings it back in. And all these, if this thing is spinning, if it's spinning with the prop, then that's going to convert it right back into this straight flow instead of this. And of course, that's what submarines try to, they call it cavitation. You know, where they create out of the tip of the props, actually creates these air bubbles if they run them too fast. So there's millions of dollars spent in the designing of props on the submarine. This is a magnetic flow sensor. These depend on fluids that must be somewhat conductive. And most fluids are, right? You know, most fluids will conduct an amount of electricity. So what we have is we're moving the particles through the pipe. And this has got to be a non-conductive pipe. And then what we have, so now we have, what do we need to induce a voltage? What do we need to induce a voltage? In motion, yeah. So we need a magnetic field. And do we have that? Yeah, right there. Yeah. And do we have a conductor or something that can conduct? It doesn't necessarily have to be a true conductor. Okay, so that would be the fluid itself, right? And then number 3 would be what do we need? Motion. What determines the amount? Strength of the field, but we're not changing the strength of the field, right? Okay. And number 2, we're not changing what the conductor is. No, yeah, the amount has nothing to do with the size. Y'all understand that? Now, if the size would determine how much current we could get out before the voltage starts dropping. All we're just saying, okay, to induce a voltage into a conductor, we need to have a magnetic field. We need to have what? Conductor, and we have to have motion. What determines the amount is the number of conductor loops. Okay. Now, if we have a lot of conductor loops and we use a really fine gauge wire, if I took my voltmeter and hooked it up to it, I would get a lot of voltage. If I came up and hooked a true load to it, it might drop to 0 because what did I just do? Now the resistance of the wire comes into play. Y'all understand that? But it has nothing to do with the amount. It depends on how much current we can get out of it. Does that make sense? So the size of the wire does not determine the amount that we get induced into it. We still get the same amount induced into it. It's just now the wire is dropping the induced voltage. Does that make sense? So the gauge of the wire has nothing to do with how much is induced into the wire. It determines how much what? How much current we can get through the source. But we're still getting the same amount of voltage. It's just that the voltage is being dropped between. Does that make sense? And then, of course, the speed. That's what we're looking at, the speed of the motion. And what are we changing here? Yeah, we're changing the what though? Pairing the speed. So what happens is these little sensors out here, and that's what they're sensing. They're sensing the induced voltage. So the faster it's moving, the more voltage it would get put out, right? And the slower it's moving, the less voltage it put out. But it's gotta be conductive. This wouldn't work with like distilled water and anything that's probably been distilled. So they probably have problems with alcohol, stuff like that. So the distilling process, one of the things of the distilling process is what?
Takes the minerals out.
Gotta taste the minerals and all the impurities, which is what's conductive. So distilled water is non-conductive. You'll understand that. And so if we try to use distilled water here, it wouldn't work unless we deliberately induce. So how does it conduct in your battery? You know, you're supposed to put distilled water in your battery in your car. You got a lead acid battery.
Right.
And now it's supposed to put tap water in there because it's got all that gunk in there, right? All that lime and stuff.
That's the way everybody.
But it's, yeah, and then they wonder why their batteries get going out. And they take them apart, it's got all this goop down in the bottom, shorting out the plates, right? So that'd be like not scrubbing out your commode every once in a while. You ever seen the gunk that just builds up on that? Well, that would be. So what makes it conductive is the acid. Acids are conductive. So acids are conductive, and what you're doing with the water, you're setting probably what we call the pH level of the acid. Most of the time you're okay if you just fill it up above, but if you really work with batteries, you have a hydrometer you put in that thing, expect the specific gravity of it to make sure you have the correct acid to water ratio. But yeah, you need to keep you a jug of distilled water if you want your batteries to last a long time. And we had guys that said, I had a dead battery. I said, did you check the water in? He says, no. The last one we're going to look at is ultrasonic. We have two types. We have what we call the Doppler effect. And then we have time of flight. It's pretty easy to see. The Doppler effect, the transmitter and receiver will be mounted on one side. And then a time of flight, they'll be mounted at an angle. So what happens is that we're going to send out a sound burst, and then we're going to look at reflection, right? Understand? And of course, a Doppler effect, that's what it does. What is Doppler? Well, what does the Doppler radar do?
Echo.
Well, our radars work on that.
Waiting on the response
It senses air, though. It senses that movement in the air or something.
That's what it does. It senses movement. That's what Doppler does. It senses different. And Doppler radar is actually sensing air moving in opposite direction. So that's why the display looks so weird. So they'll bring up the radar and it looks like this. And they'll bring up the Doppler and we start seeing most Dopplers use lots of colors. Red and green usually. And that's where you get into trouble when you see those red and greens colliding right there together. They call it coupling is what they call it. That's what James calls it. We have a real tight coupling because they're looking at speed, but a Doppler looks at speed moving in two different directions. So what we do is we shoot out an ultrasonic, and then that's all we're doing. We're looking at a phase shift in the speed, right? That makes sense. The problem here is we got to bounce it off something. So it depends on the sonic conductivity, particle density, flow profile. And it's also it also is affected by temperature, density, and viscosity. So these guys are unsuitable for these guys are unsuitable for really, really accurate measurements. But they're real fast because, I mean, you can get the heads that are just mount together and you just strap them on. These guys, the time of flow, those things have just about got to be put in there perfect. And it depends on the diameter of the pipe. So the spacing that you put, so you'll see a lot if you look them up where they've actually got a measuring thing on it so you can measure out the placement. What's nice about the time of flight is they measures time. These guys are what? Bi-direction. Unaffected by what?
Temperature.
Yeah, these guys are accurate between 1%. we got some, pictures. So these, if you see these things strapped on here, then this is what?
The sensors.
These are Doppler, right? You see it inside one unit like that, and those are Doppler, right? Okay, I'm saying. Now this is time of flight. You see where the sensors are mounted?
45 grand or so.
I don't know what the angle is. That would probably be
22
.35. I don't know.
and a half. Yeah, 45.
That's a. But notice this would be a temporary one right here. You can stamp it on for a pipe. But what you do is you look at these things in a wad. Yeah, they're in an angle like that, and it makes no difference which blade.
we installed one something like that on
This one?
Uh-huh.
Yeah, that's what it is. It's Doppler. It's pretty easy. You probably had to get a rotor out. Or did you do it?
Yeah, we had to make sure that was certain
Certain
distance
distance.
apart.
Yeah.
Then we had to strap it to the pipe,
Strap to the pipe.
and it was detecting our flow rate of acid coming in to the vehicle, coming into the tank.
If it's a pretty clear liquid, it don't have any impurities in it, it moves like that, these guys are pretty good. But, you know, if you get any type of particles or anything in like that, or bubbles in fluid. Now these guys here have bubbles in the thing. You got bubbles in the fluid, so if you got bad flow or sucking in air. I don't know if y'all seen that. If you ever work with a swimming pool? No, just trying to seal up all the little holes, because the water's moving through there, and if you got a hole, odds are it's not going to squirt out. It's going to do what? It's going to know. It sucks those bubbles in, and if you get bubbles in your pumps are not as efficient, right? Y'all ever seen that? No, I'm talking about in the hosing. So if you can see the hosing, we had an above ground hose. And so we used the plastic hose that you could see through. And you'd get that thing running and you'd see bubbles.
Oh, flowing through, okay.
Coming into the pipe, right? You understand? Because it was moving and those pipes are corrugated so you can stretch them. So what you had is you had a hump, then you had a hole, and if the hump was down inside that little valley, it would literally do what? It would suck air in, then you get air in your system. You know. Not near as efficient. The pumps are not near as efficient. Well, that's why a lot of even underground pumps will have a bowl somewhere that's clear, so you can actually see the flow. And if it's got bubbles in it, it means you got what? You got a hole somewhere. And guys, that's it. This is an animated GIF. I couldn't find one on that. So what do we go? Is any problems? Most of them. And what advantage does these have over? Okay, or these last two have over the other ones that we went through? Well, I'm talking about what advantage does these two, that's one, over these. So you're right, no moving part. What else?
It's just one pressure.
Just one pressure, but these guys create a pressure differential. And it does that by impeding the flow itself, right? You understand? So how does the valve work? Well, the valve works by impeding the flow, right? And we change the size of the orifice, we change the flow rate. We don't change the pressure. People don't understand that. So when you control your pipe outside, you're not changing the pressure, you're changing the flow. Because if you can turn that thing on in a trickle, and you can leave, and if you've got the end of that pipe stopped up, it's gonna eventually do what? Build up, and it's gonna be out just like it was, no matter what the flow rate. So controlling the pressure and controlling the flow rate are two different things. So when we control the flow rate, if this thing is feeding an actuator, if we control the flow rate, what do we control on the actuator? We control the speed. of the actuator. And of course, if we control the pressure, then what do we control? The force, not the flow, the force, right? So the flow rate determines how fast the actuator moves, and then the force, and then the pressure determines how much force the actuator can generate.
Say that one more time, the last part. The force, if we control the force, it can.
Controls the pressure. No, we don't control the force. If we control the pressure, we control the force. So the formula for force is what? What does that have to do with the flow rate? The flow rate's not in the formula, right? You understand that?
Do some stuff to
How can you do some stuff to that?
it. I feel it.
Yeah, I don't know of any law like, on our power formula, what we do is we substitute the Ohm's law into that. But Ohm's law says D is equal to I times R, right? I don't know of any formula that says P is equal to any type of flow anywhere, or A is equal to any type of flow. So the amount of pressure we generate determines the force. Okay, you understand that? The flow determines the speed, speed, or velocity, or whatever you want to say. So if I had not a good example, but the motor determines how much current it gets depending on the horsepower. So we have, in hydraulics and pneumatics, we have these little flow valves. And just because we change the flow valve doesn't change the force. It changes the flow rate. But we're talking about the actuator. It changes the speed of the actuator. And then we have other valves called pressure control valves that operate on pressure. And we use those to control the force. Two different things. If you get into hydraulics and pneumatics, you should pick up on that real easy. We used to calculate how fast, we had a big old cylinder on our hydraulics. And it was, good gracious, like 32-inch stroke on it. And one of the things on one of the labs we did was calculate how long it would take to extend and retract, which is pretty neat. And we didn't use the pressure, we used the flow. We had a flow meter on there, so we could measure the flow rate, and we would calculate how long it would take to extend. And if you wanted to make it extend faster, you can't change the pressure, right? Understand? With the same load. And of course, if you reduce the load and increase the pressure, it is going to move faster because the flow rate will auto. That makes sense.
Wow. Wow, back in.
Oh yeah, but it was pretty neat. It was a pretty neat lab. You hot in? You hot? Yeah. Okay. Okay, guys, y'all got any questions on that? And the review for the test probably won't be available up to like, I've got it up to 237 questions.
Well, wait, by the time we got paid.
The last 6 1 for it, right? So I used to hate those tests. I used to really love that. That's test 3, and then the final is Tuesday after that. Okay. No questions on this?